Hello, my name is Rob Reynolds. Welcome to Calculus Section 3.7, where today we learn the chain rule. And the chain rule is useful when you have composite functions, a function within a function. And then 95% of the time, not always, but usually we'll let u be the inside function. And then after you find u, then it's important to think about who's du. So that's what this discussion is about. Instead of doing the derivative of dy dx, we're going to create this du, and then we have an extra du dx. So this is that notation for what's happening. And again, why I can do that is because I'm just multiplying the numerator and denominator by du. So here's the actual rule for the chain rule, and it says take the derivative of the outside, that's there, write down the inside, that's there, times the derivative, this is my du, times the derivative of the inside. That's the extra little du that sometimes students forget. And then when we take the derivative, we don't want to forget to decrease the exponent, but then the times the derivative of the inside. So this, I guess, is all green, because when you write down the inside, you have to decrease that exponent by 1. Let me show you an example. Well, I have other, I don't know, I do this for the n class, but so the derivative of anything to the nth power is n times you take the derivative of the outside, there you go, write down the inside, don't forget to decrease the exponent by 1, times the derivative of the inside. So this is my little du. And we learned in a previous video that the derivative of e to the x is e to the x. Well, now it's e to the cow is e to the cow d cow. And we learned in an earlier video that the derivative of cosine cow is negative, because it starts with the letter C, negative sine cow, but then we just have to remember the d cow. So here's your first little example. It's the derivative of the outside, so that's how they get the 15. And then they say, oh, just let this be something. So I'll call it junk. So it's the derivative of the outside, don't forget to decrease the exponent by 1. When you write down the inside times the derivative of the inside. And all of this I'm going to be referring to as the du. And there's all sorts of little comic strips about this. You can read this and laugh, but this little penguin guy, that's my little du. That's the little baby cow, or the baby calf. All right, enough of these examples. So 90% of the time, it's a good strategy to try. And then so you might want to ask, well, what happens if that doesn't work? And we'll come across some examples there as well. So here comes the first problem that we're going to look at, trying to let u be the inside. But I'm just going to follow that definition. I don't even have to do a u sub for this. I can just take the derivative of the outside, write down the inside, don't forget to decrease the exponent by 1, times the derivative of the inside. And the derivative of 5x plus 4 is just 5, and you'd probably write the final answer as 15 times the quantity. And you probably don't want to multiply that out. It's already in factored form, which is the simplified version. Now, take close note of notation here in yellow and here in green. These are two different problems. And I didn't write any parentheses on purpose because I want you to figure out where the parentheses lie. So for this one, it's understood the parentheses are here. And for this one, it's understood that the parentheses are here. Whether you write them or not, you need to know. So let's start with part B, the derivative of the outside. So y prime is 3. Write down the inside. Don't forget to decrease the exponent by 1. So that becomes 2. And then times the derivative of the inside. Well, the derivative of sine is cosine. And honestly, that's my final answer. I don't think I want to do it. You might just rewrite this as sine squared x cosine. But it's the same thing. So this guy, though, it's the derivative of the outside. So the outside function is sine. So here, the derivative of sine is cosine. Write down the inside function times the derivative of the inside. So my final answer here, I'd probably throw the 3x squared. I don't know why. It just looks better as this. So two very different answers. And yep, the author got the same result. So here comes another one. It says version 2 of the chain rule. Well, I don't know what that means, but we're still going to take the derivative of the outside, write down the inside. Don't forget to decrease x by 1 times the derivative of the inside, 18x squared plus 3. And then this is factored form, but oftentimes you'll see them multiplying that together. You can leave it factored for because I kind of like the factored form. When you see radicals, just like before, let's get rid of the radical by writing it as 5x squared plus 1 to the 1/2. So then the derivative of that would be the derivative of the outside, write down the inside. So when you decrease the exponent by 1, it goes to negative 1/2, and since they times the derivative of the inside, and then since they started with a radical, we'll probably go back to a radical. So everything here in yellow, the negative exponent says put it back in the denominator. And well, I can reduce this too instead. So I have a 5x in the numerator, and then in the denominator, I have the square root of 5x squared plus 1. And then part C says the derivative of the outside, write down the inside. Ooh, this problem's going to take just a little bit. Why? Because now I need to take the derivative of the inside function, 5t squared over, and why did I say this is going to take a little while? Because this baby cow is a huge baby. I have to actually do the quotient rule. So I actually have to do low d high 10t minus high d low all over low squared. You can see where I'm going to go with this problem, but for the sake of the video, I'll let you finish this up. Maybe I better, because I see something that's going to happen that we should probably discuss. So let's see, low d high minus high d low. The derivative of this is 6t. So what I thought was going to happen, I don't think it is going to happen anymore. I thought maybe we would have another factor here that I could cancel something. See, I can't do this because that's part of a sum. I can't factor. So I guess this isn't as bad as I thought. You do probably want to distribute this and make that 25 times 3. So that's going to be like a 75t to the 4th over 3t squared. And so this squared gets multiplied by this squared, and then you would probably end up with, since nothing canceled from numerator and denominator, you'll probably end up with a 3t squared plus 2 to the 4th. Let's just see what the author has. Of course, you have to, well, good, the author did the same thing. So some things must cancel, and so go ahead and work on that and see if you can't get that numerator 15,000. So if you haven't printed off the handouts, go back to Blackboard, and I have PDF files where you can work on this. These are always interesting problems. Reading this chart, it says find the derivative of the h function and evaluate it at 1. Up here, I've defined the h function, or the author has defined the h function as a composite function, f at g at x, and so we're going to actually just follow h prime 1. Here's just literally the definition. Take the derivative of the outside. I'll just write it out for you. Write down the inside times the derivative of the inside. So I'm just going to let a be 1. That's what they tell me to do first and foremost. So then I'll try to just read some things from the chart. So I'll start with g at 1. And so I'm going to come over here, and there's my 1. G at 1 is 2. So I'll say f prime 2 times, now I'm ready for g prime 1. So I'm going to go to the g prime and look at the 1, and I see that it's a 3. Then I'm going to try to find f prime 2 from my chart. So there's f prime. I'm down here at the 2, so that must be the 7. And 7 times 3 is 21. And then you could repeat this process for h prime 2. Again, you should have a handout. You try that, see what you get, and I think the answer is going to be 20. 5 times 4 is, you should get down to something like that. And again, I think the authors worked it out here. There it is. Perfect. So if you can't get that, then that's where you go and you shoot me some emails and I'll help you do that. So again, more chain rule of powers. This is exactly what we've been doing. So the derivative of the outside, write down the inside, decrease the exponent by 1, times the derivative of the inside. Well, the derivative of tangent, if you remember from a previous video, is secant squared. And the derivative of 10 is just nothing. So I think that's it. The order that you write these answers aren't really important. A times B times C is the same thing as A times C times B, but no worries there. This is kind of an interesting problem. We know that the derivative of e to the x is e to the x. And we also know that the derivative of e to the u is e to the u, but then we tag on a du. Well, actually what's happening here is there is a dx over here as well. We just don't ever write it because dx divided by dx is 1. So over here, it's du divided by dx, but we usually don't write it. We just usually write it as du, but I could also write it as u prime. So all of this is just notation for, it's the same notation. Du dx is the same as du as this same as u prime, just different ways to write it. So feel comfortable with all of those. So here we go. This problem, I'm going to do a little let u. So let's let u be that little inside function. This is kind of actually I've got a function within a function because I also have the sine function. So you may think that the inside function is this. In fact, let's back up and let's let that be the end. So let's just take the rule and then I'll do a u sub in a minute. The rule states the derivative of the outside, which is just cosine, write down the inside, and then times the derivative of the inside. So this is kind of where I was heading before. How do you take the derivative of this pink inside guy? And my suggestion would be, let's do a u sub. So let's let u be this inside function, which is e to the u. So I'm going to be applying this definition now. And then whenever you have a u, we got to remember we end up with a du. That's that baby calf, a little baby penguin lesson. So the derivative of this is right here. It's e to the u, and I've let u be cos, times du. And du is right here. I've already worked that out for you. And then you just bring this down. So it's the cosine of e to the cosine x. And then, so this is one term. So I can't I'm looking at this thinking, well, maybe I can multiply e to the cosine times e to the cosine, but that's not the way it's written. It's written where this is the cosine of this angle times this times that. So I might throw the negative out front, but I can't multiply the e to the cosines together. Let's see how the author wrote it. Yeah, throw maybe the negative. He even threw the sine x out front, but in fact, he threw all this out front and then times this. But again, the order that you write your final answer is less important. Here's the chain rule and the product rule. I'm going to do 1d2 plus 2d1. You can do the derivative of the first, write down the second, plus the derivative of the second, write down the first. However you do product rule, that's fine with me. But I'm going to do 1, and then the derivative of the second. Well, when I think about this, this is really an exponent. So the derivative of the second is 1/2 the derivative of the outside. Write down the inside times, don't forget to decrease the exponent, times the derivative of the inside. Plus, write down the second function. Well, I'll just leave it, x squared plus 1 to the 1/2 times the d1. Well, d1 is the derivative of the first, and the derivative of the first is just 2x. So we have a couple choices here. How to simplify this. And the first thing I see is that I do have a common factor. And you always want to, when you do greatest common factor, you pull out the smallest exponent. So I'm actually going to pull out this -1/2, and you're going to say, oh, wait a minute, this is not a -1/2. How can you pull that out? I'm going to say, well, you can, and I'll show you how in a second. But you also have a 2x that you can pull out. Looks like that's common. So again, I hope everyone sees there's two terms here separated by this addition sign. And from those two terms, I'm going to pull out an x² + 1, the smaller, which is -1/2, and I want to pull out a 2x. And then whatever that's left with will be in here with this little plus sign in between. So I literally, when you do a greatest common factor, that really just divides each term by the greatest common factor. So, geez, I have this 1/2 around here that I really love to get rid of too. So can I not factor out this 2? Can I just pull out an x instead? And the reason why I'm looking at that is because this 1/2 cancels with this 2. So instead of pulling out 2x, I'm just going to pull out an x, and I'm going to leave this 2 in there. So I'm just going to pull out an x. So these x's cancel. The 1/2 and the 2 are gone. This is all, it looks like just that x² is left. And then from here, if I pull out an x, it's gone. Now this guy is not all gone, but it does greatly simplify because x to the 1/2 over x to the -1/2, you rewrite the base and subtract. So 1/2 minus a -1/2 means it's just x to the first. So this becomes x² + 1 plus this 2. If you want me to write like this, I can. So maybe I've got 2x² + 3 in there times all of this out here. Let's see what the author says. So let's see, maybe if we play around with this a little bit, this negative exponent, of course, goes back into the denominator. I think we're almost there. And then I think the author took this x and distributed it throughout. So let's see if we can't just get what he did. 2x³ + 3x. I don't know why he didn't leave it in factored form. And then, but I do agree, let's get rid of negative exponents. So that goes back into the denominator, x and the square root of x + 1. And that is what the author had. I like this answer, but personally, I would have just had that x still floating out there. I definitely would have gone back to the radical, gotten rid of the negative exponent because they started with a radical. And that's just the general rule of thumb. So again, good, but I would have factored an x. There are many more problems on this assignment, and I would encourage you to work through them on your handout. I've got worked out solutions showing you how to work them out, and I would encourage you, let's keep going. This one has several U subs. It's kind of like the movie Inception. It's a dream within a dream within a dream. So you're going to have to do a U sub within a U sub, because I see this inside function, and then this function is inside this big old function. And so practice this, because this is another. You can see I've got a function within another function. So you're going to have to do a couple U subs in here. So practice those on your handout. And if you have questions, feel free to email me as normal, and I'll try to answer your questions. Good luck